Now we'll see the equivalent focal length of combination of two thin lenses separated by a finite distance. So equivalent focal length of combination of two thin lenses separated by a finite distance. Let us take now here two thin lenses. These two thin lenses are separated by a small distance, and the principal axis is passes through the center of the two lenses. So therefore now here these two lenses are separated a small distance or a finite distance d. So therefore now the ray of light is incident on the first lens and emergent from the or refracted from the first lens, and then it incident on the second lens, and from the second lens the refraction will takes place, and then that will hit to the principal axis. And if that ray, that whatever the emergent ray from the first lens is moves towards that principal axis and hit to that principal axis, that is focal point f1. It means if the second lens is not present, then that converging light is located at this point. We are going to say like this. So now here for the second lens, this is the incident ray. Second lens, this is the incident ray. So this incident ray is not parallel to the principal axis. So therefore that focal point is not located on the principal axis. So this point is there. That point is converging point, but it is not a focal point. So now this is the B is a ray of light incident on the lens, and then next this is the C is the incident light is incident on the second lens, and now the height of that lens will get, or a height of the object will get, that is h1, and here this is the h2. So now what we'll do here, we'll increase this incident ray. First incident ray, that is parallel ray of light to the principal axis. So and next another one ray, that is emergent ray from the second lens, will increase in the backward direction. That ray is cuts to the incident ray, and then will give that point is a P, and will draw one perpendicular line on a principal axis which is cuts to that point of P. So now here we will get two interior angles, that is one is from the incident ray, that is a delta 1, one is from the emergent ray, that is a delta 2. So this angle is equals to this backward ray of that emergent ray, delta 2. So this angle is this angle, both are same. So from these two rays, which is emergent ray backward in the direction of backward, and then the incident ray is creates an angle, that is exterior angle. So here what you will get, the exterior angle is the sum of the, that is exterior is angle is sum of the interior angle. So whatever the angle value will get, that is equals to the exterior equals to the interior. So therefore now see here, for the lens 1, what is the distance from O1 to the F1? That is nothing but the focal length F1. And similarly for lens L2, we will find the distance to the up to the that F1, that is nothing but the F1 minus D. So here distance is there and it is a minus to the that F1, and then we will get the distance, that is F1 minus D. Let us now take here, let two thin lenses L1 and L2 having focal length F1 and F2 separated by a distance T. So now here we will consider two triangles. One is this PCB, one of the triangle we will consider here. Triangle PCB or a PBC. So for this triangle, the exterior angle is equals to the sum of the interior angle. It means the angle deviation, that exterior angle is nothing but the angle of deviation is equals to the delta 1 plus delta 2. So therefore now here delta is nothing but the height divided by focal length. The deviation formula is h divided by f. So therefore delta equals to h1 divided by f1 plus h2 divided by f2. So this is the equation 1. Now from this figure, what is the deviation? The deviation is nothing but delta equals to this deviation, delta equals to h1 divided by h1 divided by f. h1 divided by f. It means, see here, the height of that h1 complete from this point to this point, that is similar to this one height. So therefore h1 divided by that f. So now h1 is height of delta and f is resultant of focal length. F is resultant of focal length of a system. So the equation 1 becomes h1 divided by f equals to h1 divided by f1 plus h2 divided by f2. So this is the equation 2. Now we'll take another one triangle. In triangle BO1F1 and another one triangle, that is CO2F1. These two triangles are the similar triangles. See here, I have drawn the diagram. First one is a BO1 CO dash F1 is a one of the triangle, and similarly CO2 F1 is a another one of the triangle. Both are the similar triangles. So here the height h1 divided by f1, and the next from the triangle second one, that is height h2 divided by distance f1 minus d. So therefore from the triangle 1 and 2 we'll write h1 divided by f1 equals to the h2 divided by f1 minus d. So therefore the h2 equals to we can write f1 minus d divided by f1 into h1. So this is the equation 3. I think 3 or 2. Sorry, 3. Now for the value of h2 into equation 2. So we'll get h1 divided by f equals to h1 upon f1 plus f1 minus d divided by f1 into h1, so divided by f2. Now h1 get cancelled. What remains here? 1 divided by f equals to 1 divided by f1 plus f minus d divided by f1 into f2. Simplify the equation here. 1 divided by f equals to 1 divided by f1 plus 1 divided by f2 minus of d divided by f1 into f2. So this is the equation equivalent focal length of two lenses separated by a small distance. So in this relation we can find the equivalent focal length, otherwise first length of the focal length, second length of the focal length, otherwise we can find the distance between the two lenses separated by a small distance. That is we can find by using this relation.